Right, here we are again, another round of Martin Viesbeck. Sorry for that, but unfortunately I only am with you here today, so that's why you have to get both lectures on the first day. This one I entitled to discussing with you a few opportunities about integrated ocean observing. It has some elements that we've covered already in Annie's talk, which is actually good. So we can see where we look at it from the same angle, and maybe you get some additional perspectives. But I thought I say a few words about what's for me home. So I work in Kiel as a marine scientist, and we actually have a network of marine science. And I just wanted to give that, not that everybody needs to come to Kiel, but just as an idea maybe for what you could do at your place. So I'm working at GEOMAR, it's the Helmholtz Center for Ocean Research. It's a marine lab. I'll show you a few words about it in a second. But we've realized that it's great to be an oceanographer and do all the great things, but if you really want to look at marine science in a more holistic sense, it's kind of useful to work together with all the faculties at Kiel University. We also have an Institute for the World Economy, so we're working with economists, and we also have a School of Fine Arts that we're working with on outreach and visualization and issues like that. And all I'm saying, depending on where you are, in most locations, you have interesting possibilities for collaboration. Seek them out, look for them. We've been doing this quite successfully and been able to do much broader science than we would have done otherwise. But my own research institute is the Hermes Center, and our mission is to understand the physical, chemical, biological, and geological process in the ocean. Very much like your typical large-scale marine institute. We're pretty significant in size, 1,000 staff. How many people work here in Esrin? A little less, right? Yeah, so we're slightly bigger than Esrin, but similar. And so we have quite a few PhD students and scientists, and what we're kind of proud of that we collectively spend 600 days at sea. And if you can turn that into money if you want. So when in Germany, we are quite lucky to be part of ESA, the European Space Agency, so we have space data, but we also can go to sea and collect data from the ocean. And here you get the 5 more significant research vessels. There's another one, a polar icebreaker called Polarstern. And what's interesting for us is that anybody in Germany, any scientist can get access to these vessels. You have to write a proposal, you have to ask for ship time. So it's open for all of the science community. These are not vessels which are run by a particular institute. So we operate 1 or 2 of them, but we operate them on behalf of the science community. So every university scientist can write a proposal to get access to the ships, which we are very keen on. I think it's a very good system. In other countries, university owns a vessel, and then only the university employees can work with them. And I think that's not so scalable. Then we also use an increasing range of equipment, which is more robotic. So you see a few of these types in the pictures here. Some of them are deep diving robots, like top right can go down to 6,000 meters. We also have a manned submersible left called Argo. It doesn't dive very deep, 300 meters maybe, but for some coral research it's kind of really exciting. And then we have big AUV fleets that we can use for underwater surveying and reconnaissance. And for example, that thing in the middle row left there called Abyss here, it's a 6,000 meter Remus AUV, an underwater vehicle, which has a bathymetry charting device and also cameras. And this particular thing that you actually see there was our robot that discovered the lost Air France plane, that went from Rio to Paris, and halfway in the ITCZ sank into the Brazil basin. And so it took us, together with Woods Hole, 6 weeks to find it, and our device found it. And took some pictures that I don't want to share with you. We also have big equipment here. But then I thought I'd start after lunch to talk to you about what you have to accomplish at a summer school, right? I like Calvin, right? Just remember, Kevin, those who didn't learn the mistakes of history are doomed to go to summer school, right? So I guess you're doomed because you didn't learn of the mistakes from history. But also for summer schools, I wanted you to keep your personal summer school scorecard, okay? So every day evaluate, talk and meet fellow participants. You know, you might want to collaborate them with in the future. I shared it last night with some of you. My first summer school I went to, I still work with half of the attendees today in big international projects. So remember, these things can be really life-changing events. Second, communication, and meet all the senior people. That means Annie and me. And senior in parentheses, not because of age, but because of elapsed time in the business. And because it's a chance. It's also true for some of you are postdocs and some of you are master students. These successful postdocs will soon have a junior professorship and they'll hire PhD students. That could be you, right? When you're a master student. So make sure to network with them. It's really important. It's good because otherwise you could be online and looking at it from at home, but then you don't meet everybody, right? The advantage of being here is you meet people. Sometimes it could be, for example, communication. Make sure you get your point across and listen to the argument of others, right? So that's good communication. And education, take full advantage of the breadth of this wisdom across the school. Learn something new and exciting every day. So don't just speak to the people who also work on Sentinel XE, right? But actually make sure to talk to everybody who's here because you might learn something that in hindsight turned out to be the most important thing of the whole summer school. And that wasn't what you expected, right? So that's my scorecard. What I really want to talk about is 4 things. Why is science internationally organized? How is ocean observing organized? Annie went through some of those points. So it's a bit of a dummy's guide to the ocean alphabet soup, maybe. And then I'll mention a few specific things that we have, that we heard some about and some not. And then at the end, I'll mention a conference that you could be participating in if you want to. So first question, why is science internationally organized? Seems difficult, right? You gotta meet people from different cultures. They might not speak your language. You have to agree on a common language. Why would anybody want to do that in science? So before I answer that, you have a minute with your neighbor to discuss that. Why do you think scientists organize internationally? And then we can look at it together. So you have a minute of talking time. Okay, so the minute is over. That always goes fast when you're enjoying yourself. So who has the best answer? Yes.
We just think that ocean is not private, it's global, so why to say at our house?
Okay, another good answer. It's not private, it's global, yes. Yes, here's an answer right here.
First point that my friend mentioned was money. You need a lot of money to work together.
Yes.
Secondly, science, to answer one single question, it's important to collaborate between different sciences, actually. So different scientist communities working together for one solution.
Yeah.
And unless you're organized,
okay.
it's
Good answers already. Nobody mentioned the coffee that you can have together or the pasta or some other great things, fish. So I think the main reason is that some problems in science are so big, so hard, so difficult, just like what you were basically saying, that even an outfit like where Annie works at CLS or Toulouse or GEOMAR, so we couldn't do it, right? Even if he took all our resources. And for example, prominent examples are climate change, right? Even a single smart person couldn't answer that. There's some questions where a single person can definitely do it, but there are some other questions in science that just can only be done collaboratively. And sometimes there's a resource issue. For example, when you have CERN, like a big accelerator, we cannot afford to have one in every country. But sometimes it's the question that is so hard that you need to involve all sorts of insights to get there. But you should forget. I mean, it is costly, right? It doesn't come for free. So if you can avoid it, please avoid it, right? But there are certain questions where you cannot avoid it, and those are the ones that you want to focus on if you want to do international collaboration. The other thing I want to mention is is the universality of science. It is kind of interesting that the language of science, has a certain universality to it. There's a few other things that we all breathe and eat and things, but the scientific way, it's not everybody agrees to it, but a lot of people do it, and there's very few countries who, at the country level, say, we don't think science is part of us. Right? There are certain countries who put science higher and others put it lower, that's for sure. So there's a universality of science. And what's interesting about science should be about freedom, inclusion, equity, and authority. And in particular, I think I also wanted to make that very clear for the summer school here, that we operate at a bit of a code of conduct here. That means, everybody's voice counts, right? Regardless from where you come from, what your background is, what your personal skill set is, and so on. So this is equity issue. Freedom is very important for scientists. We want to kind of speak our mind, meaning we think we have a certain argument, and we want to be able to say it, even if it doesn't bode well with a political opinion or societal opinion or something like that. It's just a scientific hypothesis or, quote, fact. We want to be able to discuss it, equity and authority. So there's groups out there that trying to promote that or that try to ensure that that happens, and one of them is the International Science Council. So it's an international organization usually supported by either the academies of sciences in your country or your science research ministries, but there's also specialized unions, as we say. This is the oceanographers, the atmospheric scientists, the plant scientists, the soil scientists. They have unions sometimes. And the International Science Council really wants to promote the one voice of science, scientific freedom, and address issues that bring us together as scientists. This could be insights that we want to see change in society, but it could be mobility for scientists, which we don't always have, that scientists can travel to meet and to exchange their view. So that's sort of what the International Science Council does. But it also supports particular activities, and I'll mention one or two or three of them, some of them that Annie mentioned. So ocean and climate research are good examples of international science. Ocean is huge, right? I mean, there's just no way for one country to do it. Climate is very challenging, no way for one country to do it. So then the questions, how do we go about that? So ocean or climate. So I'm going to show you a little bit of how that internationally happened. So climate has a connection to weather. And in weather, we have an international organization called the World Meteorological Organization. So that is an organization that was founded in the 50s. And why was it founded? Because in 1950, thereabout, there were the first groups of people who said, I can forecast the weather. But it was very quickly obvious that if you wanted to do a weather forecast, it needed to be a global, at least a big network of a hemisphere. Otherwise, you couldn't make progress. So it was very clear, if you wanted to do weather forecast, either everybody works together or you're not going to have it. And that was enough of a motivation for nations to come together and start an organization called the World Meteorological Organization. Its main function was to exchange quickly weather data on observations so you could make your forecast. Right? Later on, it added other elements too. So, and what it does do, it also supports research. For example, the World Meteorological Organization also supports the World Climate Research Program that Annie mentioned. It also supports the global climate observing, and the global ocean observing is part of that. I'll mention some of those in a second. And it also has a climate services program. So it's an organization that is serving the members, in this case countries, on a need that they have articulated, right? In this case, it'll be weather forecasting or climate. But how did the World Meteorological Organization get into climate? So in 1979, they hosted the first World Climate Conference. There was never a climate conference before, 1979. For you, that's a long time ago. I can vaguely remember that. I'm trying to remember what I did in 79 in school or something. So, and the first World Climate Conference started the World Climate Program, which then became the World Climate Research Program. And the main reason why it was set up, because member states, countries around the world, heard about this climate change thing. They had no idea whether that was true. They had no idea to measure it. They didn't know how to go about it because individual scientists in their countries just didn't have enough power to do it. So they came together to do that. And they did it for a few years. And then after 3 or 4 years, it became apparent that maybe there is something to this climate change thing. I mean, individual scientists had been talking about this longer, but it became maybe an issue for society, maybe not. And then very quickly, they set up this intergovernmental panel for climate change with the idea to provide these assessments, to provide reports to government what is known about climate change, because they weren't sure that the individual scientists in their country knew actually what was going on. They just weren't sure, right? So they asked the international community to tell them what goes on about climate. So this is the outcome of the first World Climate Conference. Then there was a second one in 1992, so 20-some years later. And in 1992, they realized if there really is something to it that climate is changing, we better have the observations to show that. So before 1992, there was not an international agreement to share climate observations around the globe so that you can actually plot these great records that Annie has shown you some of them. So, and then that second World Climate Conference started the Global Climate Observing System. It's an international effort where nations agree to share the data, which then collectively could tell you whether the planet is warming or not, whether rain is shifting, species are migrating, and so on. And then, at the same time, in the 90s, they started the UN Framework Convention on Climate Change, because then, after the first IPCC report, they said, well, maybe there is something to it. Maybe climate is changing. Wouldn't that mean that we have to act together, that we have to come to a solution? And the solution organization is the UN Framework Convention for Climate Change, which has these conference of parties, these COPs, and in the COP21 in Paris, they did the Paris Accord, right? So that's where it all started. So it only started in 1902, that it was big enough of a problem that the nations agreed to do something about it. The third World Climate Conference was in 2009, and that was the last one. There were only 3. And in 2009, the countries around the world had realized that indeed climate is probably changing, but they were more now interested, they have a weather service, which tells them every day how the weather is going to be the next couple of days. But they were more and more interested in a climate service. Who tells me whether El Nino is happening, a drought is coming, how bad climate warming is, all the kind of things that we know from weather between day 1 and day 14. They wanted to know from climate from months 1 to 50 years, say. And that was then called the framework, Global Framework of Climate Services, which is also what WMO does. So I'm going to show you, because Annie mentioned a little bit, would I talk about adaptation and mitigation? I'll show you just one slide to this. So when you talk in climate to policy people, at the bottom, which you cannot read so well, is the Global Climate Observing System, Earth observations for you, right? That's observations. And then the World Climate Research Program takes those information in the climate context and discusses all the climate issues. And it has 2 streams of information. One feeds to the assessment, which every 5, 6, 7 years a major report gets written. The assessment, IPCC, informs the United Nations Framework Convention on action for governments, carbon tax, whatever, to mitigate that. So that's the mitigation route. Or World Climate also research informs prediction information centers, El Nino prediction, rainfall, droughts, things like that. That then informs climate-sensitive sectors and tells them what to do. Stock up food, build dams, things like that. So these are adaptation measures, right? So you're dealing with the consequences, that's adaptation. Mitigation is you're trying to put a problem, you capture it at the root. in this case is CO2 in the atmosphere, right? That would be mitigation. And the climate framework services sits there. And that internationally didn't exist. Climate services weren't internationally organized up to as recent as 2009. And they're happening now. So now I'm coming to more the summer school. So how is sustained climate ocean observing organized? So I gave you the big picture. Obviously, the information observation is key to these services. So how does that get organized? So that's also, unfortunately, a bit complicated. So observations are technically organized in three. There's two major groups. One is the global climate or global ocean observing system. Actually, let me do the middle here. Global climate observing system. So, and the climate, as Annie said, has three spheres. You have the atmospheric watch, you have the ocean and the terrestrial side. So they're shown here in these sort of logos, for a little bit different. And then a few years later, another group came about called the Group on Earth Observations. It's slightly differently set up, similar goals. And so both the global climate observing system and GEO, the Group on Earth Observation, both touch climate. GEO touches many more things, land, biodiversity, many other elements, while the climate observing system looks only at climate. And now these groups don't come from nowhere. They get what we call sponsored. So sponsored means somebody looks after them, that they're doing proper work. Again, coming back to science. So the Global Ocean Observing System is sponsored by three organizations. One is the Intergovernmental Oceanographic Commission of UNESCO. And now you see why it becomes complicated in our world. There's the UN, and it has the United Nations cultural organization, scientific and cultural organization, UNESCO. And it has an ocean part to it called the Intergovernmental Oceanographic Commission. All right? But they felt a global observing system for ocean and climate needs to have an ocean, so this group was mandated to do that. They're around since about the 60s. In the 60s, people realized oceans is becoming an issue. Who takes care of ocean in the UN system? So they set up this Intergovernmental Oceanographic Commission. It's member state driven. Then, as I said, there's the Group on Earth Observations, much more recently launched, only in 2005. Simply put, few governments said, oh, these UN organizations are too slow, too formal, too governmental. Let's do something else. So they set up this Group on Earth Observation, which is non-governmental. So they can have stakeholders, they can have industry partners in that. 10 years later, you kind of wonder how different they are. But anyway, that's what was set up. And under GEO, there's a program called Blue Planet, Ocean and Society, which also supports the ocean observing system. So we're getting closer to many acronyms, and you don't need to read all of them. So the Global Ocean Observing System, which is really looking after ocean observations, is supporting the permanent ocean observing system, but also modeling and analysis of the data. And the sponsors are listed down there. It's the IOC, the Intergovernmental Oceanographic Commission of UNESCO. It's the World Meteorological Organization. It's the United Nations Environment Program, and ICSU, which is now called the International Science Council. They just changed the name this summer to make your life even harder, right? But you see, what's important is, why is it important? It's very good that a science organization, International Science Council, supports GOOS, because that means that scientists have some say in what gets organized. It's not just done by governments, right? There's independent civil scientist societies there. It's good to have IOC for the ocean and WMO for climate there, and the environment program obviously there too. Now, a program like them has many acronyms. So they have a General Assembly GOOS, then they have a steering committee, and then they have panels. So what does that mean? It means you have, ocean observing is a huge task. And so they organize it by dividing into three spheres. One does physics, one does biology and ecosystems, and one does chemistry, biogeochemistry. Because they just feel there's different things you need to do for chemistry than for biology, than for physics. Different groups, different networks, different capabilities. So they set up three different panels. And then there's some stuff below that I don't want to go into except for one. And then there is implementation. That's just like we heard this morning for ESA, you say this is what a satellite should do, and then there's the guys and girls who actually run the mission, and the satellites and the data downstream. And the people who run the mission is called the Joint Commission, great name. You wonder, what is a Joint Commission, right? like a conference of parties. I mean, okay, conference of parties can be anything, right? So we call it COP, Conference of Party 21. Everybody knows, oh, that's the Paris Agreement, right? But anybody else with a right, you know, like again, the receptionist at our hotel, oh, I'm visiting at the Conference of Parties to number 21. They're like, you're mad, right? These abbreviations only work for expert communities. So JCOM Ops, everybody knows an ocean, but what it really is, it's a technical commission that makes sure that technically the stuff that I'm going to show you in a second works. And they are making sure that the right sensors get used, they're using the same calibration procedure, that they're reporting the data, that they get shared, that it's all fair, and so on. And so how does the community get to these organizations? And the way we do it in oceans is kind of interesting. The World Meteorological Organization is very scared by this. And Jerome, where are you? There he is. So Jerome has been part of that club of gangsters. So the ocean community decided, no, we're going to organize ocean observing bottom up. I mean, scientists get together, meet at conferences, and decide what we're going to do, and then we're going to talk to the World Meteorological Organization and ask them to support us a little bit, and ESA and so on. So in Ocean Ops, there has been a big conference in 1999 that Jerome organized, and ESA supported as the lead sponsor. And so what we do at these conferences, we get together and then decide what do we have, what do we need, and how can we get there. And at that conference, that happened to be in a nice place, right, in Venice. Well, no surprise, Jerome organized it. And we identified that somehow we weren't systematic about ocean observing. People did certain things, but they weren't systematic. So then we devised a very simple framework for ocean observing, but it could be done for terrestrial atmospheric observing. And the framework is like this. What do you need? Question is who? What do the scientists need? What does the World Meteorological Organization need? What does UNEP need? So you basically say, what do you need? You could say temperature, salinity, sea level. You know, you put the requirements down, and you also ask a bit why. You know, is it for government purposes, for economic purposes, whatever. These are the requirements. And then from these requirements, you decide what's essential. In the middle, I'll explain all the boxes in a second. In the middle here, you see the process. That's the stuff in the ocean, satellites or in situ. We'll talk more about that. And then once you've got all that, you have to make sure that some of the stuff in the ocean produces information. That means all the data gets collected, calibrated, and put into a joint database or data stream, so you can, you know, do your scientific analysis, run a model, do a forecast, whatever that is. So that's the simple thing. And then if you ask people, what do you need? You know, somebody says, oh, I need crabs, I need phytoplankton, I need the deep bioluminescence, I need some chemical 1,000-meter depths. You get lots of wishes, right? So, but then the idea was, so what are the essential ocean variables? And essential is a negotiated quantity where we basically say most scientists say they want that. Most stakeholders say they want that. And ESA can measure it, or some in situ person, right? So that's what we call essential. Essential is not necessarily the like to have, but it's what we could have, given the resources, technology, and so on, and what most people think we need. These are called essential ocean variables. And so we derived some of them, and then each of these groups does the essential variables of physics, chemistry, biology. And then we go through ideas that you are very familiar with. Some things are very conceptual. In ESA terms, these explorer missions. You try a satellite, you see, oh, I think we can measure salinity. I'm not sure, right? So you do a concept. Now, once you're flying a science mission and you see, oh, indeed, we can measure salinity, that and that and that, then it becomes more mature. You do either a pilot or you do a sustained observing. It's also true for in situ. So these, we call them readiness level. You hear them a lot in satellite speak, TRL, technical readiness level, or SRL, scientific readiness level. It basically refers to how ready, how clear, how sure are you that you know what you're doing. In science, we sometimes try things out very new. We don't really know what we're doing. We have a hinge, right? That's the concept. But sometimes we know exactly what we're doing, and that's mature. So it's a complicated structure, this framework of observing, its requirement, what to measure, essential ocean variables. In the middle is all the kit. Talk about in a second. Data assembly, data information products, issues, impact. And again, if you don't deliver the data back to the citizens who with taxpayers' money paid for the observing, they're not going to give you the money for the next mission, right? So every element has to work, otherwise you don't have much. So this is, but in order for us to do that, that's why we need international frameworks, because every scientist does something in some corner, somewhere here, or somewhere there, or somewhere there. We work somewhere individually, but the system, as a system, has to deliver, and that's why we organize things. That's why a lab, like in Toulouse, or my lab in Kiel, we just couldn't do it. It's just too complicated. That's why we need international organizations, committees, meetings, blah, 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 and acronym soups that come with that. So I thought I'll give you a little bit of a taste of what are the elements of the space observing, which you saw already this morning. You're going to hear much more in this week. So I'm going to focus on the in situ stuff that supplements the space. But remember, you'll hear more about space. So here's a global map of colorful dots, and each dot is for some technique, ship, robot, buoy, whatever, that measures something in situ in the ocean in the months of June of this year. So this is what GEOMAR does. It actually gives you access to almost real-time information. So you know exactly what was going on this month, at least with those data which get reported in near real time. So so the ocean looks pretty well covered there, right? But don't be fooled, right? It means one observation per month sometimes, and so we'll take that apart a bit. So the first network, which I can go over quickly because Annie has covered it, so these are the tide gauges. So certainly for sea level rise, they're very important, but now we have altimeters, so we can measure sea level from space, and the tide gauges are still important because they can help us to calibrate the altimeters, and as you also see here, some of them are coastal. But the colorful dots say, when they're red, that means some countries said, yeah, we have a tide gauge and we'll make the data available, but they never send the data. Right? And then there are some yellow ones where the data shows up 5 years later and so on. So you'd like this map to be all green dots, but you can clearly see they're not, and this is a few years old. But a more current map wouldn't look that dramatically different, so we constantly have the problem with data sharing. In space, that's not so much a problem. Yeah? You have one satellite, which has one sensor, one data downlink. You either get the whole map or you don't, right? But in situ, many countries, many actors, many reasons why a certain measurement doesn't show up, right? And it can be many reasons. What you can do with that, as Annie showed you, you can document things, for example, like global average sea level change, or with an altimeter, you can also map as the spatial distribution. So we heard all about it this morning. So that's one network. We call them a network. So it's a network of tide gauges working together with the altimeter to give us things like sea level. Another network called the Global Surface Drifter Network. So this is the map from July 23, so last week, of buoys out in the ocean, which we call surface drifters. They're very simple equipment. So you see that chap over here deploying one. It's a little plastic ball, a flotation, and has a string attached to it, and then it has a holy sack, so it's just a drogue, so the ball doesn't fly with the wind so fast, so it stays put in the ocean surface. This thing is usually at 100 meters, 150 meters deep, and on the top of this, it has a thermometer at the bottom and an antenna at the top, so it basically transmits sea surface temperature and the position. And we have about 1,400 of them, and half of them have also a barometer on the top, so they measure air pressure. And these devices are used for sea surface temperature measurements in situ, which are the anchor point for satellite sea surface temperatures. So whenever you grab a sea surface temperature map from a satellite, the satellite agencies are very keen on this network because it ensures that all your atmospheric corrections and all the things you have to do to your radiometer get done properly. So it's a calibration for the satellite system, and for the pressure, it's also used for weather forecasting. But it's very hard to keep that network up and alive. I'm sure you noticed that there's very few buoys here in the middle of the Pacific or in the middle of the Atlantic. Exactly that place where Annie said El Nino happens. Well, what's the problem here? In the ocean, the oceanographers know that this is a region we call upwelling, which means water comes up and pushes the stuff to the side, right? And you should notice that these surface drifters always collect here, there, and there. They're doing exactly the same thing as microplastics, though, right? They just get pushed by the surface currents into what we call convergence zones. And so every month or so, they're putting new buoys out here in the middle to get at least some information over there, because they don't last there. They get drifted away, right? So any passively drifting network has its problems because you can't actively navigate them. They're just drifting. They go with the flow. They do what the plastics do. But they're very useful networks, and they can also measure surface currents by the drifts of these things. But that's the surface. Now let's go deep. And Annie showed you a little bit about what happens deep. So for deep, we have the Global Hydrography Network, which is called GOSHIP. It's also a great name. What does that mean, right? So GOSHIP brings together scientists and so on. So the idea is that scientists who go on big research vessels, like you see the Argos, the Meteor, and I think it's the Ravel. Should have put the Tommy Thompson, but anyway. So these are ocean-going research vessels, and sometimes crazy ocean scientists go across the oceans, like here, go from A to B, and every 50 kilometers stop and make a measurement top to bottom. And they measure with these systems the carbon content of the ocean, temperature, salinity, oxygen, many other things. But again, it's a big ocean. My lab can afford 1 or maybe 2 per year of these sections, right? But if you want to get global coverage, you can only do it by international coordination. And wouldn't it be terrible if the US went across and I went across the same time, right? We would waste 1.5 million euros of ship time to measure the same thing, right? So that's why nobody would ever do this without international coordination, because you're running the risk of wasting a lot of money, right? So that's why we have international plans. We agree on who's going to do what line, and then you try to execute that plan internationally. It's not centrally funded. Everybody has to bring their resources to bear. And what can you do with this? For example, you can look, here's one example, cutting through the ocean from the Arctic to the Antarctic here. And when you see it blue, the upper 3 kilometers, that ocean water got fresher. When you see it red, it got saltier, blue fresher. And for us oceanographers, we can say, oh, if the water gets fresher, it probably had rained more. And if it gets saltier, it evaporated more. So it's a massive rain gauge. And if you look at the IPCC assessments of climate, you find that these data, looking at ocean salinity, are a very important reference point, because there's actually not even a known way how to observe rainfall over the ocean. You can try many different ways, but none of them is accurate. And the satellite-based measurements of precipitation, as you well know, are also quite full of errors. They get calibrated on land. So it's kind of hard, actually. 70% of the planet has no rain gauge to know how much rainfall was falling when and where. And this integral of ocean salinity helps you, at least for the long trends, to learn something about that. It's also why SMOS, these salinity emissions, are quite helpful in that regard. So what they also learned with these global hydrographic measurements is that the ocean is warming. And I think from the last IPCC report, I think the most revealing figure to some of us was that here is shown for the last 50 years or 40 years, the evolution of energy on the planet, not temperature, energy. That means where is the warming happening in terms of energy? And when you see the atmosphere is this purple color, you can't even see it. It's so thin, it means it doesn't take much energy to warm the atmosphere by the 1 degree that we saw. Because its density is so low, it doesn't have much heat capacity. It's much harder, for example, to heat the soil, land. That's the orange here. You see a lot more energy was used up to heat the soil. Because the soil has a higher heat capacity, it's much harder to heat soil. The white one is ice. That's the energy it took to melt the ice. That Annie showed you how much sea level equivalent that is, right? If you want to melt the ice, it takes energy. So that's that white bar. But all of this together is 70%, and the other 93% is heating up the ocean, because it's so hard to heat water. And what these two colors show you is the upper ocean is in light blue and the lower ocean in dark blue. And here you see at ocean depths deeper than 2 kilometers, which ocean basin has heated by how much. So we've seen through these measurements with ships from top to bottom that even at the bottom of the ocean, we see a noticeable, measurable warming. Not by much. We're talking not even 1/10 of a degree. So it means you have to have very high standards of calibration to measure that. But the equivalent is of that of 0.5 watt. And 0.5 watt is about 20% of the global warming rate, right? So there's already heating happening in the deep ocean. And the only way we discovered that was by coordinated ship surveys of the deep ocean. What Annie showed you is the heat capacity, or you can work out the total heating with sea level equivalent and mass changes, but you wouldn't know where it is unless you have a measurement there. Then we have global moorings. So these are point measurements where you put an observer in one point. It's like a balloon that's tied to a line. I'll show you in a second how that works. And it's called ocean sites. And here's a network. Maybe it's 2 years old. The figure you see in some places there are more moorings. In others there's fewer of those. And so what is a mooring? A mooring is pretty much a wire which has flotation elements. These are glass balls with air inside and instruments. This is a current meter that measures speed and direction of the current. Here's a temperature recorder and salinity recorder. So basically you put a line in the ocean and then you measure things. And one of your colleagues has been quite active in this, Nuncia, there she is. She just came back. When was it, Nuncia? When did you come back from the cruise? Last week? Yeah, from the Indian Ocean, right? So here's a picture of her ship where they were doing mooring operations, and I'll show you a little video how that works. So here is a deployment, and again, Nuncia can give you all the fun and glory details. So you put 3 kilometers of line out of the ship. In nice weather, it's kind of cool to do it. When you do it in the Nordic seas with gale force, that doesn't work. So here, and then they put an instrument on. Here's the instrument on the line. And then you keep going, and you radio to the ship operator, I guess. Here's more flotation. And then at the end here is what we call the weight. It's just scrap metal. And then that gets released. And then, poof, and you don't see much in the movie, so I have an animation for that. So then the idea is that whole thing plops down, and the anchor weight drops to the bottom of the ocean, like plonk, right? And then it stands there. And now the instruments can measure for a year or two in one place the currents, temperature, salinity, oxygen, whatever it is that you want to measure. So it's a Eulerian at one fixed point type of measurement. Now, and quite often we put them in small arrays. And again, Nuncia talked to her tonight at the reception, how you do that and what she's done in the Indian Ocean. But that's one way of doing that. Now I'm going to show you 1 or 2 results of these observatories. In my lab, we run one over here, but I'm showing you just a few ones in the North Atlantic just to get an idea. For example, there's an interest in how much water comes from the Nordic seas between Greenland, here's the ice, Iceland and Norway. And there's a very narrow gap here where the cold water from the north goes to the south. It's called the Faroe Bank Channel. And there's one mooring in the middle here. And here's the guy, Bogie Thompson, who's done all the work, and he has been working there since 1993. I want to share one short story with this Faroe Bank Channel overflow record. So when you look at the first, from 1995 to about 2000, you look at the first 5 years. Now, your eye is always a good integrator. I'm sure you will see that you can put a line like that in. Right? And if you do that, you see that there was a decline in the transport. So it's the amount of flow that goes across by about 10%, 15%, almost 20% in that 5 years. That data set, it's a lot of work to get 5 years of mooring data. You can attest to that. Got them a Nature paper. The Nature paper said the thermohaline circulation is already collapsing. That got them a lot of funding because we said, oh, you have to keep that measurement going. I wonder what's going to happen in the next 5 years, expecting that it will keep going down. And now you see, okay, if you're there for 20 years, you would have never thought that you could write a Nature paper on the decline of a transport of this series, right? But you cannot write a Nature paper after 15 years that it's stable. Nobody wants to publish that, right? That tells you something about nature journals. They only publish the wine is good for you story, and they don't tell you the other story, which is also interesting scientifically, but not so sexy from a publication point of view. So I encourage you to publish in proper journals where proper data gets published, because that's as interesting. Maybe not so sexy, but it's kind of actually more important in some ways, because what we're finding is that these overflows are pretty stable, which is interesting, right? That although climate is changing around us, that these overflows are pretty stable. Some climate activists hate it, right? They say, oh, don't do that, don't tell people that, they'll not accept that climate is changing. I'm like, I'm not supporting your agenda. I'm an honest scientist. I'm just showing you what it is, right? And then it's our collective job to see why is that, and so on. So here's another data set that happens here in the Denmark Strait. And here it's almost as long. You can see, and here you see a lot of holes. So Kirsten and Detlef, they're not poor marine scientists. They're, good marine scientists. They properly put the moorings back. But here's an interaction between the scientists and the stakeholders that we don't like. Because the Denmark Strait is one of the most heavy trawl fishing basins. If you put a mooring there, the fisherman comes by and fishes the mooring out. So they've lost the mooring 5 times in these 15 years of record, although they put moorings out which are apparently trawl resistant. There's just a little shield at the bottom where the net's supposed to be going over, but once in a while they still get taken out. So we have a lot of problems with other actors in the ocean that fishing our equipment away. And that is in the tropics almost even worse these days with longline tuna fishing who kill moorings. And our work is here at the export of 53 North. That's part of the deep overflow. And again, we're seeing 15 years of bit of variability, but no trend. So that's really interesting. Now, the climate models tell us this circulation should slow down by 20% by 2050. But for the 15 years we've been measuring it, we didn't see it. I mean, it's not supposed to be very visible, but it's good to know what the variability is so that then, the generations after me can look at this long record and then decide, did climate change the way we expected or not? So these are just baseline data, right? We're putting them in places. What's good about this place, it's not very noisy. So if there was a change of 20%, we would probably see it. In other places, it's too noisy. So last network I'm going to show, it's a bit of the poster child of ocean observing. It's called Argo. And Argo, I could go into the name, I don't. It's a network of profiling floats. So these are robots, again. But these robots, here's me in a rubber boat, here's one of these Argo floats, they're as tall as I am. And what they can do, and Annie has shown you some of the results, but what the robot does, it has inside a pump, which can pump oil from within the robot into a rubber. It's like a neoprene rubber, like a wetsuit thing. It pumps about 120, 150 mil of oil inside the bubble, in the oil bladder. And so what it does, it increases its volume, by pumping oil out. So same mass, bigger volume. That means the float changes its density. It becomes lighter. So then it's like a hot air balloon. It just goes up. On the way up, it turns its temperature, salinity, and pressure sensor on. And from 2 kilometer depths, it measures a profile every meter or every 5 meters to the surface. Once it's at the surface, the antenna has a GPS receiver and a satellite transmitter. It sends an SMS home to the operator, and then it sucks the oil back in and sinks down to 2 kilometers depth. The next thing it does for 10 days is nothing, is save energy. Because we want this robot to last long, so it takes a lot of energy to pump and a bit of energy to transmit. So in here you can see a little animation of how this network of robots evolved over time. Now we're in September 2001, and we have 320 robots in the ocean. And I want you to look at this movie a little bit, and isn't it fascinating to see the geopolitics of marine science? Look at where all the floats are and where they're not. Right? So we're a few years into it. We are 600 floats. In 2002, there's not a single robot in the South Pacific. No commercial vessels, hardly any researchers. You just couldn't get the robots out. There was nobody who was willing to throw it in the water for you. So then we're at 2003, still not a single robot there. Right? So then they said, we've got to do something about that. So they talked to these ship operators and say, let's hire a research vessel. So here's one, here's the second one. Right? So the research vessel just dong, 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 puts all the robots out. So we can, same thing here in the South Pacific, you see here in the Indian Ocean, right? So these robots, they can only get into the ocean if we go there with a ship in some way or form. It could be a commercial container vessel, it could be a research vessel. And so now in June 2004, I moved from the US to Germany, and I wrote a press release, said, oh, we have 1,500 robots in the global ocean, isn't that exciting? Not a single newspaper picked up the press release. I thought, how boring of these guys. Now newspapers like it a bit more. So we were halfway there, and so I'm going to spare you that. So as of yesterday, we had 3,758 of these robots in the ocean. So each robot, every 10 days, measures the upper 2-kilometer temperature and salinity profile. Some of them will do a bit more these days. And now you can see by now we've managed to finally catch up with our satellite friends, right? It's a truly global observing system. Usually the problem is with in situ, it's only patchy, and the satellite gets the whole thing, right? But the problem with satellites is they're just at the surface. They can only measure surface properties or integrals like mass, but they couldn't measure in situ. So, and let me just show you why physical oceanographers are so excited about this Argo business. Here I'm showing you depth, time, 1880 to 2000, temperature observations per month in some sort of nonlinear color scale. So here you see, there was a few early expeditions where they did quite a few observations, the Challenger times. Then not much, and then in the 20s and 30s it became popular again. But by and large, less than 100 temperature observations per month everywhere of the globe, average around the globe. So then when Jerome and I got a bit more grown, we started the World Ocean Circulation Experiment here in the 80s, and at least we got 100 or so at depths here. But then Argo, as I showed you, started about here, and then when it took off, by now, it takes about 10,000 or by now 12,000 profiles per month compared to what we had before. So you see an order of 100 or so more information about the deep ocean coming today from robots, telling us what the ocean looks like. And that allowed us to do graphs like Annie showed to you, that we can measure the global ocean heat content, in this case, from 0 to 2,000 meters with pretty good accuracy because of these little robots. And it's such a central quantity because remember, 93% of the energy of global warming heated the ocean. That is the array that can measure that can document whether climate change is stopped or not. I mean, we know it will not stop, but at least we can also show it. So it's really exciting to have these robots. And for example, these robots could give you, if you were interested, a map of the temperatures in 1,000-meter depths now. There's not too many societal actors out there who need to know urgently what the temperature in 1,000-meter depths is. But some scientists find it very cool. In particular, my biology friends find it really very cool because they want to know whether whales react to this and things like that, right? So there's certainly people who are interested in that. So the combination of remote sensing and in situ really allows you to get a full picture. That's what's saying here. The combination of Earth observations, that means from space and in situ, are really needed to look at the whole ocean system because there's certain things we can do from space, but not everything. And as Annie was said, there's a few challenges on the horizon. High spatial resolution. Now, we're learning more and more about small scales in the ocean. You saw some eddy pictures this morning. And that's very hard for in situ because, ships are slow, robots aren't so many. So space is really one of the resolution. And there's some interesting missions planned, and I hope that one or two of them will get to see space. I mean, the satellites will get launched. Then I think there's a new challenge on distribution of ocean pollutants. I mean, this has to do with carbon. Where does the carbon go in the system? Things like oxygen loss. Annie talked about pH changes. Deoxygenation is another area, but also plastics. And this today, almost every week in almost your random newspaper, there's a comment about plastic in the ocean and things like that. And it's interesting. The ocean community doesn't really have an observing system in place to really show you in a coordinated way how much plastic is where. There's many, many projects that sample it in some way, but they don't do it in an agreed way. So some take bucket samples, some take net samples, some take big nets, small nets, long nets, short nets. They count the plastics in there, but you don't really know. You can't say, is it per volume, per area, per time? So there's no coordination. So global coordinate observing systems would have a procedure, a manual, how you do the observation, so that regardless which nation or which ship or which observer does it, it's always done the same way. So then you can compare the data and produce a global map. We're nowhere near that with plastics these days, and that's why they're also looking for space to see, could you do something from space? Maybe you couldn't detect plastic, but with the currents from space, you can at least see where it all goes and maybe where it came from. So I think Annie talked about coast. Coast is where people live, and there's much and more interest in learning more about coastal change, and they're going to look for remote sensing to aid local measurements. So, and as Annie said, when you get close to the coast, some of your sensors on a spacecraft have a very hard time dealing with this very hard transition from land-based electromagnetics to ocean-based electromagnetics. And the transition zone is very hard to properly sample, and there's a lot of interest in doing that better by whatever way. Annie told you about some technology options. There's some scanning techniques people want to use and so on. But I think that's another opportunity. But I really think the biggest opportunity of all is to really improve our fusion of data sets into information. And I think all of this you will hear about this week. Marie-Helene will talk to you about all of these topics, and I think you're going to learn also a little bit hands-on how that's done. So, but it's certainly an area. So if I may, just 2 more short comments. So this shortcoming is realized, and I'm running an EU project called Atlantos. And again, international coordination, we do it because we have to. I can tell you for sure, it is no fun to coordinate 62 partners, right? With also the legal documents and so on. But it's great to work with 62 partners because now we have covered a lot of countries, all European countries, and also Brazil and South Africa, the US, Canada, to really think about how can we do better in integrated ocean observing. And I thought I'd show you a little
Atlantos,
movie.
Improving Ocean Observation. We draw great benefit from the ocean. Think of food, transportation, beaches, energy, and climate, all of which require a dynamic, well-balanced ecosystem. But we also harm the ocean through overfishing, oil spills, ocean acidification, and plastic waste. The ocean can also harm us. Storm surges can flood cities, and tsunamis can destroy entire coastlines. Future changes in the ocean could greatly affect us. To improve our stewardship of the ocean and prepare for or avoid future hazards, we need better ocean observations and understanding. Until now, observation has been conducted through loosely aligned arrangements of national and international efforts. We lack coordination, bringing together the data from many sources, buoys measuring wind and waves, ships surveying fish stocks, and satellites providing the view from above. We waste time, money, and energy by not working together. Observations should be shared widely in order to integrate data sustainably and efficiently. These problems are not new. We have a framework for ocean observing, a guide to help us decide what to measure, but it lacks practical application. We need an improved system to gain the crucial knowledge necessary to respond to significant ocean changes that are coming. For example, protecting coastal communities from storm surges by measuring tides and wave patterns. The EU project Atlantos wants to improve Atlantic Ocean observing. Supported by an international team of ocean researchers from around the Atlantic Basin, this effort aims to strengthen international collaboration through sharing ocean observations and promoting engagement and innovation. Our vision is to work with the ocean community to build a coordinated, efficient, and sustainable system. The legacy will be a blueprint for Atlantic Ocean observing.
So that's just a little advertising for the project that we have. So we're really trying to improve the way we do business, and there's many work packages, but I just want to show you the idea. The idea is, again, you have the societal requirements. It could be aqua farming, storm surges, ship routing, oil spills, climate change, things like that. And then we go through all the motions, essential variables, networks, data streams, data sharing, data assimilation, support networks. And at the end of the day, we want to generate the information that allows us to realize these societal benefits. But again, for one person, that's very hard to do. So we're doing this as an international coordinated network and thinking about the institutions that it takes to do that efficiently. That's not only done in the Atlantic, it's also done for the Southern Ocean, the Indian Ocean, Mediterranean, Pacific, Arctic, and so on. And just for Jerome and me, life never stops. So Jerome, 10 years have passed almost from Ocean Ops 09. So we're planning for Ocean Ops 19. And it's going to be in September this coming year, so 19 and 16 to 20 in Honolulu. And I think what's exciting is these conferences in 99, we started, Jerome, remember, 99? And it resulted in the first international system for physics, ocean physics. Then in 09, we did biogeochemistry and biology. And I think in 19, we really want to connect these observing systems to user needs. And we also need to think a bit more about better governance arrangements. Notice also we went from 300, Jerome, where we almost knew everybody who came by first name. With 300, you can barely do that, right? That's like 3 times of the summer school. That was all there was internationally. When we went to Venice, we already had 650 participants. And at that point, it was a bit hard with the first name basis and shaking hands, but I think it was still a bit of a family affair. And I think in Hawaii, my guesses will be 1,500 or more people coming because ocean observing is really gained in importance, interest, and it's also more actors around the globe. We have a lot of Asian countries who want to come and participate. So I invite you to come if you want to share your ideas and thoughts. But I'm going to close with my personal summer school scorecard. Thank you very much.
Are there any questions? Come on, there must be some questions. Okay. Oh, yeah. Okay.
It's mainly a curiosity question, but these robots that you put out, how long a lifetime do they have? And do you fetch them again when they don't work anymore, or do you leave them out there?
Yeah. So a great question. That's the question I love, maybe. So I'll do 3 things about that. First of all, these guys have batteries inside, alkaline batteries, sometimes lithium. It's being tougher with lithium with shipping, as you know. They can do about 150 to 200 profiles. That's the energy they have. They can do it in half a year when you do it every day, or they do it for 4 years if you get them to do every 10 days. Now, once they run out of battery, they run out of battery usually deep because the most energy is the pumping. They get stuck. So what we're doing, we're polluting the ocean with aluminum batteries and sensors. We're not too proud of that, but economically, a robot like this costs, depending on the sensors, something like 12,000 euros, maybe 14. But if I would go and fetch it, which theoretically I could, right? But there's 3,000 out there. That means every 300 kilometers, one. You will have to catch it when it's up because it won't wait for you. And a day of ship time, you need a big ship, cost you a day, one day, 15,000 euros. So the economics would be very tough, right? So what we are working on glider systems, which can navigate themselves, and they could go back to a home base. But I'm sure that's 15 years away. So for the next 15 years, we'll be actually polluting the ocean with a bit of metal. Now, I can give you excuses. For example, do you know how many container vessels lose every year? 3,000. Right? So compared to that, this is nothing. That doesn't make me proud, but it's the economics that make us pollutants, and there's nothing too hazardous inside of them, but it is pollution. And one trivia question. I know there's some engineers and physicists here in the room. So these 4,000 robots here, how much energy does it take to run them? So think of, like, you know, when I was young and a kid in my grandma's living room, she had a big lamp, 100 watts, right? Bright lamp. Water cooker, 1,000 watts. Small car, 10,000 watts. How much energy does it take for 4,000 robots. 100 watts, water cooker, 1,500 watts, small car, 10,000 watts. Jerome should know. I don't know if he knows. If nobody raises his hands, I'm going to ask him. Yeah, some of the 3,000, all of them together. So
I'll let people guess.
he's shying away.
Not much.
So the answer is 80 watts, 80. That's it, one light bulb. And that is what modern electronics can do for you. That's what technology innovation can do for you. You can have a global observing system in situ, diving 2 kilometers deep. All it takes is the energy of one light bulb. But we are polluting, I'm sorry for that.
But they're very slow.
Yeah. What do you mean slow? They measure one profile every 10 days. Or 4,000 every 10 days, yeah? But still.
They're slow going up and down.
Yeah,
So
they're very slow.
If you wanted to make measurement faster, you would have to put an engine instead of just buoyancy.
Yes. Okay, there's 2 more questions.
Just a curiosity, if you integrated the observation with the satellite for the correction both way.
When we integrate it with the satellites,
Yeah.
would the correction work both ways?
Yeah, I mean, the observation that you take in your lab with
Yes.
your project, if you integrate with satellite
Yes.
measurements
Yes.
for, I mean, the correction of the satellite to improve the...
Yes. Oh, we do it both ways. So as Annie was showing to you, that has become really, really very helpful for both finding problems with the in situ system, but also finding problems with remote sensing or finding new things that we're missing, right? So, and most scientists that I know, marine scientists, definitely use all data sets they can get their hands on, and indeed they are really helpful to correct and watch out for each other, so we have the highest possible quality. And quite often we find odd things in one or the other data set that was really helpful, and we would have not found it without the other checking on them. So yes, but also, as I said, at the end of the day, scientists, societal actors want information. They don't care where it came from. They want the temperature, the salinity, the current, and I think fusing of the data is really what we need to do in the future, plus error bars. But you learn about this summer school.
Thank you. Who do the Argo floats send their data to, and how available is that data?
Yes. So if you want to be part of the Argo network, there is a bit of a formal thing you have to do. That means the data get transmitted to whatever is programmed in the float, which is usually a phone number of the operator. The Europeans tend to send all the data to the Hermes Center directly in France. They do it for Europe. There's one in the US. But within 4 hours, the data are on the internet. Sometimes also faster than that. So it's free and open for anybody. And there's 2 data streams. One is what we call the real-time data stream. Again, that's in a matter of hours because it's used for weather forecasting and so on. But there's also a quality-controlled climate data set that usually is 2 years later, because that's where they're also checking for faulty sensors and things like that. So there's a lot cross-buoy checkings and so on. So that usually takes a year or 2. So that's why we're providing 2 data streams. One high-quality delayed mode and one very fast real-time data set. And all the nations that are part of it contribute, including India and China, who sometimes have problems with sharing data in real time. But in Argo, they do it. So, which the oceans are very proud of, the oceanographers, that we managed to even get some of those countries who have a hard time with data sharing on board in this network, because they see the benefit. It's as simple as that. Okay, one last question back there, and then you guys have to work.
And you said the data is only temperature?
No. So the core Argo mission is temperature, salinity, and pressure. Okay. Pressure is for vertical, right? But then there's enhanced sets that can measure oxygen, they can measure chlorophyll, can measure turbidity, and some of them are measuring pH already.
It would be so interesting if we had nutrients.
Yep, there's also a nutrient sensor on some of them, but again, then you're talking more energy consumption, less profiles, but yes, they are available. And my guess is in the next 10 years, you'll see a big growth in these other types of networks. But there's a bit of competition because we want these climate-driven floats to last long, and if we put lots of sensors on, they're going to last only half a year. So then we have to figure out what a good compromise is. But yes, there's also there's a nitrate sensor that we use. I use them on gliders. It's a different technology that doesn't go so deep. We have a Zuna nitrate sensor. Yes, they're there. So anything you can do on a sensor which doesn't have much power, you can do it. It's just a platform, right? You can put lots of stuff on. Okay, I think, Chris, I've extended my welcome here.
Okay.
You should probably take over. Thank you.
Thank you. Okay.